So I'm kind of out of time, probably because I talk about the cats too much. So today's lecture, I'm gonna try to entertain, I'm gonna infotain you, because as someone who is active in research, I can tell you some cool things about lasers. And so that when you are in the field, so many of you are engineers, I want to tell you a little bit about the lingo and the type of technology that's out there so you don't seem like a doofus. You know, one of the cool things is when you're in your first job, you're on equal footing. Oh, that's great. Not really, because you're on equal footing with people who've been there 20 years. And you're expected to be equal to them. You're not. And those older people are going to take advantage of that. So I want to tell you about some things some of the terminology you may encounter that would put you on the same level as your peer group. But at the same time, today's going to be kind of wacky. I'm just going to tell you stuff. I'll put this on the extra credit, number 3. This will be the extra credit, number 3. Any of you got any questions, like what's up or anything, or who are those people? I'm kind of curious. We're all okay? Okay, so again, just remember, come by tomorrow for regrades. All right, so today's is just cool stuff about spectroscopy. Spectroscopy, as much as all right, I am grading your exams. Where does selections rule come from? I accepted the angular momentum of light, that worked, or you could have, this is one of the times you could have mentioned something. Now I know I don't want you writing equations for that, but put this in written form. It comes from the difference dipole equation. Is it 0 or not 0? That's where selection rules come from. So anyway, a lot of you blew that. I was kind of shocked because that's all you had to say. Put it in the right, or even if you wrote the equation, I would have taken it. But anyway, when it comes to spectroscopy, that's all that it comes down to. Is it 0 or not? You just put in the different dynamics that occur at these different energy ranges, the wave functions thereof, and see whether you get a 0 or not. So it's unbelievably simple, but so much details that it fills a whole class. So that's why I don't really want to try to even get into it. Not even if I had a week, but I really want to even start trying to get into all those details, like rotational spectroscopy only works if the molecule has a dipole. It's like HCl. It's a gas phase spectroscopy. The molecule has to have a dipole or your transition moments are 0. That's an example of the details that you don't like even write that down, okay? That's just an example of how detailed you get into with spectroscopy. Okay, anyway. With that said, I just want to re-review the electromagnetic spectrum. As college graduates in the physical sciences, you should kind of have some intuition about this. I'm just going to briefly review, talk about the dynamics that occur at these wavelengths, and tell you a little bit about one of the things that you should know is that there are all kinds of issues with generating light. All of these are photons, it's all light of different wavelengths, and you run into weird problems when you need to generate energy at these wavelengths. So remember, radio waves are made by giant towers. Towers that have scales, length scales, that are consistent with the wavelength of photons that they generate. And they work by sending electrons up and down, up and down. When electrons oscillate, they create oscillating electric fields. That's what a photon is. All the equipment we have to generate light of these various wavelengths are all dependent on our ability to shake electrons at the frequencies that correspond to these frequencies or energies. Guess what? These all have different energies, and the electrons have to be shaken with energies commensurate with the energies of X-rays for making X-rays and whatnot. Although there's a couple of tricks to this. Okay, so radio waves, nothing actually absorbs that. There's no electronic transitions that occurs here anyway. Rotation occurs here, vibration occurs here. Radio waves go through stuff because stuff doesn't absorb them. But of course you know that, that's why your cell phones work right now. Remember, cell phones are kind of like right here in the electromagnetic spectrum. That's why your cell phones work. It goes through walls. And remember, I told you the military uses that. Okay, then you get the micro radar range, and this is where rotation occurs. So there's a pecking order to to how things absorb light. Rotation is the lowest thing on the rung. That's the first thing a molecule can do to absorb light. It's very low energy. It's mostly in the gas phase. Things that try to rotate in the condensed phase, solid and liquid, it can't. So if I'm like a molecule, let's say this is water, if you're trying to absorb rotational light, you actually have to rotate. But as soon as a molecule, I actually know this for a fact, when a molecule is rotating, it can't turn more than about 5 degrees before it hits something and it gets bounced back. So that is a major impediment to absorbing rotational light, because it can't rotate to begin with. It's very hindered. Now to generate light, now this is what I was telling you. When it comes to generating photons at these frequencies, let's think of infrared and visible. Now these use the same source, which is the light bulb. Now, but you know that the problem is, since we've covered this, is that the intensity of a light bulb versus the wavelength rises and then falls according to a Planck distribution. And this is the IR. So for a reasonably hot filament, 5,000 degrees, that's as hot as they can get. You make good visible light. UV, not so much. And you know why. It's because of the Boltzmann factor doesn't allow you to... you can make UV light if you made this a billion trillion degrees, but I don't think you can do that. So you're mostly stuck in the visible. In the infrared, because of density of states, because infrared photons don't really fit inside the light bulb, it tapers off. So what do you do out here? Right? So my point is, light bulbs don't work. You can't really build small radio transmitters, and you run into the problem that gas, atmospheric species start absorbing it. So, so what I'm trying to do here is just point out that, again, for so many of you who are probably going to do some kind of monitoring, like, you know, if you get jobs in the oil industry, which is going to be a lot of you, which I hear are really good jobs. I know we think the oil industry is bad, but they're good to their employees, and I know that, because every engineer I've ever had who's ever written back to me, which many of them have, and you will too, right? They all tell me they get jobs at UP and they love it, and that's great. I love to hear that. Okay, so you're going to do some monitoring, and you got to generate light at these different wavelengths. How are you going to do it? Because again, you got a light bulb, you got a radio transmitter, but then you got this dead zone, and it really is hard, by the way. The way that this is done in your home, in your kitchen, is a magnetron. And what that does, it circulates electrons in a magnetic field, the magnetron. So it's about the size of a kind of a large softball. It's in a vacuum, and it basically just sputters electrons that spin around in a magnetic field. And electrons, you know, think about this. Okay, so I'm going to spin electrons, right? Now I'm going to spin it in the plane of your vision. Okay, and you know I'm doing that. But what does it look like to you? Let's project this vector into your plane. Left and right. Right, left and right. What happens when I shift electrons left and right, up and down? They generate photons. So there you go. That's the name of the game. Okay, rotation, gas phase, visible. Yeah, we talked about this. This is all vibrations. You've learned the quantum mechanics of this. Okay, now you get to the visible and UV. These guys work when it comes to sorry, UV is right here. I need to put a little bracket or it doesn't work. UV. UV is the same type of phenomena. The physics of absorbing visible and UV light is valence shell electron transitions. But the source of UV light is not a light bulb. You need a D2 lamp. I have never seen anyone use anything other than a D2 lamp. It's basically a fluorescent light bulb containing D2. That's entirely what it is. They are very expensive, by the way. So if you're in the field doing some monitoring, you would very likely be you'd use a tungsten and UV lamp for visible light. The tungsten light is as cheap as a regular light bulb. These are several $100s. Never leave on the instrument, not because of anything particular, because of the D2 lamp. well, for that particular. Okay, now what happens in the visible and UV are, let's say that this, now I know I'm writing out hydrogen atom, but let's just say, and then I'll even be a little bit more careful. Here's the 2p, and here's the 3s. Okay, molecules have a bunch of electrons, so let's do this. And as much as, once you have more than one electron, all the hydrogen rules are no longer valid, 100% valid. They're valid-ish. Now, the reason I'm saying that is, of course, 3 P's are up here, I won't even do the D's, is you can still think of, so I still want to draw a L plus, L minus 1 in this case, an L minus 1 transition. So, valence. All right, valence electron transitions. All right, because you're not ever going to be monitoring H atoms, ever, right? Whatever it is you're monitoring in your job, in the site, and you're using spectroscopy, you're going to have molecules. Molecules have more than one electron. They have valence electrons, and these energies are slightly lower. And so, yeah, there you go. Okay, cool thing, X-ray. X-ray are core. So here is this is an X-ray. Those are core transitions. So now typically the electron can go from a 1s to like a 3s or a 3p orbital. Typically they just get ejected. So you typically, what you make are called X-ray photoelectrons. And it has all to do, there's a photoelectric effect. We covered that at the very beginning of the class. I bet maybe you don't remember. That's fine. Let's not worry about it. And there you go. So again, valence electronic transitions are visible. Go to higher energies, and you're now exciting electrons that are just below the valence. If you ever have much exposure, it damages your DNA. You can't survive much DNA damage. That is what cancer is, by the way. I don't mean to say it causes cancer, it is cancer. So you have tons of DNA in your body. Your nucleus is full of DNA. It is very absorptive because DNA, the way DNA works is that the electrons, in the spiral, they're kind of delocalized. DNA works like miniature radio towers. They're very much like that. They're very absorptive of high energy light. So when you manage to get yourself in the front of an X-ray, your DNA is going to do most of the absorption, and that is terrible. So your body has all these DNA repair mechanisms because your DNA is constantly being damaged by light. And so we evolved that way. Okay. And now here's the cool thing. So now this is probably still kind of boring. Now I'm going to get into cooler stuff. How do we make X-ray light? Okay, now there's two ways to do it. One is boring. You can make a super light bulb. Now this is how you probably do this on eBay. You can get X-ray light bulbs. You can buy them, or you can build one yourself. It'd actually be very easy. Remember, I just told you it would give you cancer if you actually turn it on, all right? And this is what they have like dental offices. This is what they have in things like X-ray diffractometers, which we have 2 in our department. So, and all this works, and this is kind of neat how anybody ever figures this out. So you get a filament, and the filaments are just, they're just like shedders, like my cat shed fur. These things shed electrons. They're full of electrons, and they're hot. They actually literally fall off the filament. Okay, now what you have is a metal plate, and the metal plate is at a very, very, very positive voltage. So this is really simple. Now, of course, all of this is in a vacuum. The electrons shoot through. They shoot through. I have to draw this accurately. They shoot through. And then they hit another metal plate, usually copper. They hit copper. And now this guy, we're talking like, it's like plus thousands of volts. That electron punches it so freaking hard, it knocks valence electrons out of the atoms themselves. And when they relax, they outcome X-rays. Okay, so that's how they do it with in like scientific laboratories in your laboratory. Now they have another way to do this. So there's a bit of an aside, I guess I'm done with all this, which is something where I work. I don't know how to spell it, I have to bring this, I have to look at my notes. Synchrotron. Okay, there are, I forget, there's a fair number of synchrotrons in this country, but there's really only 3 in the world. One's in Japan, one's in Grenoble, France. The other one is, I can almost throw a rock and hit it, it's at Argonne National Lab. You people are only 30 minutes away from it's either second or third most powerful synchrotron in the world. It's being upgraded to the tune of $1 billion. It will then become the most powerful synchrotron in the world when that upgrade occurs. You are right down the street from it. Any of you ever worked there at Argonne? Any of you ever visited? Yeah, you visited? Cool. Did you went to the APS? Advanced Photon? You would have gone into the APS, the Advanced Photon Source. That's the synchrotron. There's really nothing else to see there except that video. Anyway, okay, here's how it works. So they have, it's a half-mile track. It's a circle. So you often see these expressed as a circle. They're not circles. It's a half mile long. What it really is a series of tubes. There's 33, 35 of them that, I mean, you learn this in geometry, that you can define a circle by a whole bunch of line segments that just get smaller and smaller. And what's happening is they have electrons accelerated by magnets that are traveling in the circle. Okay, now what happens at the circle, here's the most advanced thing. This is called a wiggler. Now, I'm going to draw this in. So what it is a bunch of magnets, north, south, and the electrons just go right through it. Now, what a synchrotron is for, it's mostly for material science. Because it turns out that exciting these core electrons, this is the spectra you get out is very useful if you're looking at something with d electrons. And again, I can't, this is where I need to have a whole class. To understand why that is, I need the whole class. But this type of spectroscopy is very good when you're looking at something with d electrons. Metals are material, metals, semiconductors, those are materials. Materials make everything that we have. So this is mostly a material science thing. Now they do some structural biology, and that just means that they use these intense X-rays to generate the crystal structure of proteins and whatnot, which is also very useful. Okay, now these electrons that are traversing, these are experimental stations. So like I say, they're like 35 of them. What happens is the electrons hit these magnetic fields, and then they wiggle. That's why it's a wiggler. So I don't think I'm drawing this right, but remember, the name of the game is to get an electron to jostle. Now, you can imagine, based on the speed, which is 99.9999% the speed of light, no kidding. This place uses more power than the city, by the way. These electrons, and they're heavy as oxygen atoms. You actually did that on the homework. That's why I had you do that on the homework, because I was going to talk about this day. They're moving so fast, they weigh so much. And then you look at the spacing between these magnets, the frequency is X-ray. There you go. So X-ray lights come out. Now, the reason that this is special is the number of electrons. So the number of photons is all about the number of electrons that you can get through this wiggler within about 80 picoseconds. That's how fast that they do it. The more electrons, the more X-rays. The more X-rays, it's a brighter source. That's the correct word. It's the brightness of the source. And that is, by the way, a technical term. Argon is like second or third brightest, and it's about to become the first brightest. And anyway, that's what they do with it. When I'm at I go there a lot, usually a couple of days a year. When you are walking in a circle, they have tricycles you can ride too, by the way, because it's so big, which is awesome. If that sounds awesome, it is. when you go through the stations, a couple of them have barriers. And they say, do not come in here, this is proprietary oil companies. The oil companies test their catalysts. This is how they characterize their catalysts. If they have a catalyst that's particularly effective and we want to know why, they take it here. And because they are also oil companies and they're very secretive, they paid the Department of Energy, which runs the facility, they paid them to own some of these beam stations. No idea what they paid. They probably paid. They told me that use of the facility is $17,000 a day. So I've been there a couple of weeks, so every day I'm there, I run up a bill of $17,000 that I do not pay. The Department of Energy pays it. What I have to do is I have to convince them that my experiment is worth running, and of course they have all kinds of people telling them the same thing, and we have to compete. We have to compete for time. So that's why British Petroleum, Mobil, Shell, they all have stations. They just bought them. So they probably paid tens and tens of millions of dollars for that. Okay, the next thing, Fourier transform. Fourier transform. Now, who's heard of FTIR? None of you. All of you have heard of FTIR. No, I'm not an idiot, right? All of you have heard of FTIR, right? Yeah, it's boring. It is very boring. Here's the thing. There's a Fourier spectroscopy for everything now. So, you know that the way that this works is you have a beam splitter, and you got infrared light, and you have different wavelengths coming in, and they hit the beam splitter. Here's a non-moving mirror. Here's a moving mirror. I'm not drawing this too well. So the light comes in, bounces here, goes through. Other light bounces here, bounces back, goes through. And then what you get is an interferogram, which looks like this. 1.0, 1.1, 0.9. It's not a big signal. It looks like this. Doesn't look like much really. And then you Fourier transform that, and then you get your spectrum. And by the way, you've basically done this before. What this is, what you're doing when you go from here to here, you're looking at the signal and decomposing it into contributions from various waves. You have low frequency waves, middle frequency, and high frequency, right? You remember that? Remember doing that when we talked about breaking down sine functions in very narrowly trapped wave functions and potentials, and how very narrow wave functions had a whole bunch of these, and very wide wave functions mostly had just this one. Remember doing that? When we did that, that was a Fourier transform, by the way. That was mathematically what you were doing. That's how I created. I had a handout on that. That's how I did it. So what you see in a Fourier transform is the intensity for any particular frequency is what you're plotting. And so these are all kind of intense. And then if you have like some in between, that's like, these are, maybe that's like right there. So again, you take the signal and you break it down into frequencies and you plot the intensity of the frequencies, and that's your spectrum. So again, you know that, but here's the thing that's really kind of cool. There's a Fourier transform method for everything now. And so let me tell you about some of those things, because I bet you've never seen them before. Because I remember when I first learned this in high school, I'm like, okay, that's kind of neat. And what's neat about it is that you're able to get all the frequencies very, very quickly. Whereas when the first FTIR was built, what they had was a monochromator, and they just did the absorption point by point. It takes about a day. It takes about 1 day to measure an FTIR spectrum, an IR spectrum. It takes about, as you did in some of your labs, it takes about 5 minutes to do an FTIR. So that's why that was like a really big deal. Okay, but now there's FT everything. So let me do FT NMR. Now, you folks did NMR in your labs, right? Yeah. In organic, did you use the benchtop one?
Yeah.
Okay, that's cool. They just added that, like right when you got here. Those just became available. They're about $30,000, but the school just thought it was like way better. So what it used to do is you would make your compound and then you give it to the TA, and the TA then put it on a rack, took it to the real NMR room, which you're not allowed in because those instruments are $1 million, and they would measure it and give it back to you. And we thought it was worth it for you to just do it yourself. I think that's fair. It is actually meaningful, although the magnet isn't quite as strong. So anyway, in the Fourier NMR, which was what you were doing, in the instrument you're not allowed into, by the way, you had a electromagnet in that little instrument. Again, I think that thing is awesome, but it's not very powerful because there's an electromagnet in a research grade. It's a superconductor, and you know, superconductors generate just massive magnetic fields. And so, BAMO. I mean, now you know all this. You know NMR is all about magnetism, and your sample is right here, right in the middle of the thing. And you do a lot to make sure that the sample is directly pointed up and down. You can't have any of this happening. Okay, regardless, here is how, when they first invented these, what happens is, of course, you have a nucleus, and if the nucleus has an odd number of nucleons, that means protons and neutrons, then the nuclear spin, nuclei have spin just like electrons do. It's the same type of spin. The thing is, if you have, let's take like helium, one proton, one neutron, it's guaranteed that those are pointed up, down. They cancel each other out, so there's no magnetism from the nucleus. If you have helium-3, it is magnetic. So anyway, so it's got a protons, right? Proton NMR. There's only one nucleon, so that's magnetic. The electrons, of course, is on the outer sphere. Okay, now here's what happens. Of course, the magnetism is pointed up. It's pointed along with the magnetic field that's created by the superconducting coils that wrap around the machine. Okay, now here's what you do that's different. Now what you used to do before is you had a radio pulse that would absorb the radio pulse and then point down, right, up or down. So it absorbs the radio pulse and you would measure that. And what you do then is you get absorption versus a different type of unit, ppm, but whatever. And you know, okay, so you can measure the absorption, the NMR absorption of a nucleon. Radio frequency by radio frequency, it takes days. Here's what this guy, they won several Nobel Prizes have been awarded for this. Here's what's happens. Don't flip it 180 degrees. It's the simplest thing. It took them a while to figure it out. They actually did it accidentally. What you do is you turn it 90 degrees. Okay, 90 degrees. So, only half turn it. Now here's the point. You're in the z direction. You know, let's take the proton, which is spin half. So it's either up or down. You're allowed to know the projection up or down. It's up or down. It's in the z direction. But what about, remember, spin is angular momentum. What about the xy direction? Are you allowed to know that? I just drew an illegal vector. Remember that before I drew this as a plate. On the test, I drew that as a plate because you're not allowed to know where it's spinning. Remember the nucleus, when I draw this, the nucleus was doing this. And so what I did was I turned it this way. So this is what it means. But notice that I'm facing this direction, but I'm not allowed to know what direction I'm facing in. I'm allowed to do that. So you know what it does? It starts to rotate. Right, now I took a little bit of a left turn, but I could have taken a right turn. So what happens is, because of the uncertainty principle, the damn thing starts to rotate. You don't even know which way. So you have to draw it spreading out. Okay, this is the cool thing. Then what you do is you then hit a reverse. You're able, you let it fan out, and again, it's doing that because it's doing this. because you know too much. When you first did that 90 degrees, you knew too much. All right, now, so again, so it starts this way, but you're not allowed to do that, so it starts messing with you. Now, what you do is, you then hit it with another radio pulse that causes it to go back. And guess what? All the samples, they started moving outward, but then they moved back inward. And so they recombined in a single direction. And get this. This is really cool. Outbursts a radio pulse from it. So here's what's happening. This is nutty. I just love this stuff though. You turned it 90 degrees, it starts doing the thing I just did a couple of times, so you're sick of that. You hit it with a radio pulse to cause it to go backward. And get this. This is one way to think of this. This state only occurred because of that 90-degree pulse. For it to reform implies the presence of a radio pulse. Now again, you started up, a radio pulse made it go down and aligned in this one direction. This only happened because of the presence of a radio pulse. You trickily made it go back into this form, but the only way that you can have this is if there's a radio pulse. But you're not adding one. You follow me? This is really strange stuff, but this is how it works. Radio pulse made this happen. It started to decohere because it doesn't allow you to know too much. You did this little trick to make it go back into this form that only exists with a radio pulse, but you haven't added one. It makes its own. This can only be like this. The magnetism can only be lined up if there's a radio pulse, but you didn't add one, so it makes one for you, and this is your detector. So you sense it's traditional to draw an eye for some kind of electromagnetic detector. Swear to God, that's how it works. It's called an echo. And most modern spectroscopies are Fourier transform echo type spectroscopies. This is one of the craziest things that happens. You'd have to look on Wikipedia, and there's really good animated GIFs on how to do a little bit better than what I'm showing you here. Okay, anyway, one other type of Fourier transform spectroscopy, let me get rid of this, actually is done in an instrument that looks just like an NMR. Get this, now you're going to love this. FT mass spec. There is a thing called Fourier transform mass spectroscopy. How the hell would you do that? Now you know that mass spec normally, you shoot something down a tube and you time it. And if it's heavy, it goes slower. You've got a little source that you have some molecules that get ionized. Here's an electric field that causes them to go down due to the due to the electric field. And if they're heavy, they go slower. Right? And there's some, geometry, you can make it do a bend and stuff like that. There's a couple of little neat tweaks. Where the hell would you get Fourier transform from that? Right? When I heard this term, I'm like, what? Mass? The answer is, you got yourself a B field, and hopefully I'm drawing this right. And you've got something, a molecule with mass, let's say it's like a DNA like I was just talking about before. Now, they have to be charged. And what happens when you have charge in a magnetic field? Right? Remember, it's a force, but not any type of force. Remember what kind of force electrons feel in a magnetic field? Yeah, in mechanics, is it a dot product or a cross product?
Cross product.
Well, you're just guessing, but yes, it's a cross product. The other word for that is torque. It torques it. Remember that? It rotates it. It actually spins around the magnetic field. Now, you need really freaking strong magnetic fields to get something with mass to do this. So what people did in Florida State, where we have the National Magnet Lab, they built a really freaking powerful magnet, and this works. So what you detect is this electrostatic charge that's traveling in a circle creates radiation that you detect, and what you can pick up from it. Right, so the frequency at which it's rotating is a function of its mass. That's kind of obvious, right? Think of the moment of inertia. Think of a moment of inertia, which is the sum of atoms and mass r squared. So of course that's going to dictate, it's all like conventional mechanics. Last bit before I get into lasers, I just wanted to tell you a little bit about, I'll tell you what, let me just get into lasers. I can tell you about fiber optics, but I don't have to say that in my time. Let me tell you a little bit about lasers. I told you I invented the world's smallest laser, but let me, this is something I really should have gotten into a little bit more. I'm glad to mention it. And this is something you really should know. This is something that college students should all know. So, and I don't know if you've covered this before, so I'm a little bit, the only thing I'm really hitting myself over the head for, but I should spend a little bit more time on it, which are, let me see if I can find I wrote my notes just for this class. Einstein, A, did I spell Einstein right? Yeah. My spelling gets worse and worse as I age. Einstein A and B coefficients. So again, STEM college graduates, you should have heard of this. Maybe you have already, maybe you haven't. So let me tell you what this is. These are kinetics. Light, absorption and emission kinetics. And that's a good segue because on Wednesday, I know a lot of you won't be here, but Cameron, right? We're going to start our kinetics bit. And again, that will be on the final because I have it if it's not on the final. Okay, so A is the rate of fluorescence. So if something is in the excited state, it will relax, emit light. Not everything is fluorescent, most things aren't. But if something is, it's easy to detect. It's like a background-free type of spectroscopy. So people, especially bioimaging people, love fluorescence. When something absorbs light, and I'll tell you how, and of course the way to measure that is you have to send in a pulsed laser. You have to flash it very quickly, not with some mechanical shutter. You don't get a light bulb and a really big shutter. That's not going to work. You have to use a pulse laser. I'm going to show you how that works in a second. You flash it real quick and then you wait and see how long it takes for something to fluoresce. You can do this with an oscilloscope, and that's about 10 to the minus 12 seconds. The rate is 1 over that. Anyway, now B is rate of absorption and stimulated emission. And here's what Einstein figured out. Basically, they're basically the same rate. That was, and this is what marked him as super genius. This is like one of the first things that he figured out just by doing pen and paper theory, that people realized that he was a super genius type guy. And then, of course, relativity equals mc squared came out. I think he did all this first, photoelectric effect as well. And this was a big deal because this led to the invention of the laser. Now what's happening here, so we call this like the B12, and what this is like is, now I'm going to do a very crude representation of something in the ground state, and we often draw light in this way. And so what happens is, this enters the excited state, and so this little mark is like a population. Molecules in the ground state, molecules in the excited state. Whoop-de-doo. Here's what Einstein figured out. That these processes, the process I'm about to draw, which is that in the excited state, if light comes by, you go to the ground state. He saw these as identical. Now the crazy thing is, though, is that while absorbing light is very easy to understand, you probably started learning that in high school, in elementary school. Stimulated emission is identical, but it will produce 2 photons. You have to have 1 photon to do it, and out comes 2 photons. And I didn't draw this arbitrary. These are what you call coherent, which is how lasers work. So a laser, you know that the traditional cavity is done this way. You have a rod which is excited, usually by a light bulb, and you have two mirrors, where one is about 50% reflective and the other is about 99% reflective. And what happens is that light starts to bounce back and forth, and then occasionally leaks out what's called an output coupler. This is called a high reflector. Okay, to make a pulse laser, you insert inside of it a shutter. So I know I said a second ago there really weren't shutters, that there actually are. Okay, this is a shutter. And this is what you call a Q switch. So the lasers I use for pointing the green ones, those are Q switch ND YAG lasers, by the way. Okay, the light source can be a light bulb. Often it's another laser. When I was in grad school, I had 3 lasers, and I swear to God, it was like a dog sniffing another dog's butt, sniffing another dog's butt simultaneously. One laser with a light bulb source energized another laser that energized another laser. That's a very common configuration, especially in scientific research labs. Okay, last bit. Let me tell you about, my laser. It's called a whispering gallery mode laser. These are something, if you Google these. Now, what I just drew here, this is called a Fabry-Perot. This is called a Fabry-Perot cavity, right? High reflector output coupler. This is probably what you learned about in high school. It turns out that its job is just to hold light inside of it. That's all it does. Light trapped plus gain medium equals laser. But it turns out you can build other laser cavities, including the one I invented, a whispering gallery mode. I didn't invent it, I just made it work right. It's a sphere. It needs to be about 30 to 1,000, which is a millimeter, micron diameter. What happens is light traverses, just like that synchrotron I drew earlier, and traverses in a circle through total internal reflection. But nothing is more reflective than total internal reflection. So like that Fabry-Perot design I just gave here with a 99% high reflector, this is actually better. Total internal reflection is more reflective than 99%. This is the world's best laser cavity, and they're small. I'm the first person who invented a stable whispering gallery mode laser at MIT in 2002, and that's why I got a job here. So I can tell you a little bit more about that, but I only got, give me 1 minute. Let me just tell you another really quick thing you can do. Another laser design. This won a Nobel Prize not too long ago. Okay, here's the high reflector, here's light waves. What someone did, a guy named Chuck Shank, he didn't get the Nobel Prize for this, someone else got it, I did that. He put a prism. He put a prism inside the cavity before like the output coupler. Strange thing, so it's bent. The cavity is literally bent at an angle. Why did he do that? Let's look at this mirror here. Let's do a close-up. It turns out that lasers are not really monochromatic. They're mostly, it's like 800 nanometers, like a nice red laser, plus or minus a nanometer. There's actually a little bit of spectral width. Now what happens is when you build a laser cavity in this configuration, the bottom is not the same. When you build a laser cavity in this configuration, what you do, I swear to God, I did this for a living, you tap one of the mirrors, and something magical happens. It's called mode locking. This is called a mode lock. What happens is the phases of all the different wavelengths of light align themselves at the end mirror. Here we go. Okay, so you see what's happening? Constructive interference means that your laser is here. This is about, say, 5 or 6 micrometers long. And then you get destructive interference everywhere else. So no laser. Laser here, a few micron in length, no laser here. Now guess what happens if you take 1 micron divided by the speed of light you get something on the order of 10 to the minus 15 seconds, which is 1 femtosecond. What happens is, when you mode lock, you get a pulse of light that is a few femtoseconds long. It bounces back and forth, and of course occasionally leaks out of the output coupler. And is only maybe about 100 femtoseconds. That's actually a good number. It's about 100 femtoseconds wide. So what you can do is pump something, hit something, DNA, whatever, with one of these lasers, initiate something, DNA damage, and then you probe it with another pulse. And anyway, so that's how we know dynamically what happens with like vision, rhodopsin in your eye. We hit it with a laser pulse. These are such fast pulses, we can actually see the molecule absorb light, change, in rhodopsin's case, it changes shape. We can actually look at the spectra of the molecule as it changes shape, and then that signal gets transduced to your nerves that go to your brain that interprets vision. It's one of the first uses of a femtosecond laser. Again, that one in the Nobel Prize. We've gone over, so thank you for sticking around. I hope this was fun. You want to ask questions? Oh, sorry, I hope you late. I hope it was fun. There's some homework in here.